Hello all, welcome to the video lecture. I'm Ramesh Lama. In this video, we'll be discussing about the graph neural network. So far, you have learned different deep neural network models and its architectures, and input to these models were either images or text. Now, if you look at the data structure of these images or text, it is stored or represented as a 2D array or matrix. So we can say it's well structured or can be represented in Euclidean space. However, data to be processed by the neural networks may not be available always, like images or well structured or that is stored in or represented in Euclidean space. So we'll be discussing about the graph neural network, which basically works on the graph data. So if we talk about the graph data, basically real world objects are often defined in terms of their connections to other things, and this set of objects and the connections between them are expressed as a graph. So our goal is to design a neural network or model that works on the graph data. So fundamentally we'll be discussing or we'll be talking about the model or neural network that will process, or the input to this model will be the graph. So the lecture of the graph neural network is basically divided into three subtopics. First, we'll discuss about the basic graph theory. Here we will discuss about the basic terminologies that are required to understand the graph theory. And next, we will be discussing about the designing a neural network that processes the graph data. And finally, we will conclude with the implementation of graph neural network using PyTorch. Now let's get started with the graph theory. As mentioned earlier, real world objects are often defined in terms of their connections with other things. So a set of objects and connections between them are naturally expressed as a graph. So in computer science, a graph is a data structure that represents a relations or edges between the collections of entities or nodes, and it consists of two components, node and vertices, and edges. Here node represents the objects or the entities and edge represents the relations. Mathematically, a graph can be defined as a G, which is equal to B and E. Here B is the set of nodes and E is the edges between them. And graph can be either directed or undirected. If there are directional dependencies between nodes, then edges are directed, and if not, then edges are undirected. We can see here that the graph on the left side is undirected graph. Here there is no dependencies between the node and edges, like the node is not directional dependencies. There's no directional dependencies between node and edges. So here it's called undirected. And on the right side we can see here these nodes are directionally dependent on the edges. We can see the edges are directed from one node to another, and so we can say this graph as a directional graph. So let's see an example of a graph. The figure on the left side shows the graph of molecule, which is nitrogen dioxide, NO2. It basically consists of three nodes or vertices and two edges connecting these vertices. Here nodes represent atom and the edge represents the bond. So the nodes and edges can be labeled. Here we can see the nodes are labeled as N and O, and the vertices are labeled as N and O, and edges are labeled with 1. One thing we can notice here is that the same label can be used to represent the different nodes. Similarly, the same label can be used to represent the edges. And another most important thing here is we can see that this graph consists of nodes, and these nodes further has a features which we call the node features. Here we can see that each nodes has its own feature, like this n node has a different features such as valence electrons, non-metal or metallic structure, and atomic number. Similarly, like here we can see for n nitrogen atom, it consists of 5 valence electrons, and its property is non-metallic property, and we can see that it has an atomic number of 7. Similarly, the oxygen has 6 valence electrons and its non-metal characteristic atom, and it has a atomic number of 8. So here what we can say that the node consists of its label and its feature. Similarly, the edges also can be labeled. So far we have seen here about the basic definition of graph. Now if we want to represent so that the computer can understand it, then how we represent the graph? So the one way of representing the graph is it's in terms of adjacency matrix, or the graph will be stored in the computer as a adjacency matrix. So the adjacency matrix does nothing but it stores the information about the it stores the information about the edges. So the elements of this matrix indicate the connected nodes, and the element will be 1 if the nodes are connected, and will be 0 if they are unconnected. We can see here, like this is the matrix, adjacency matrix, and the row and column both represents the nodes, and we can see that the node A is connected with E, so we can see node A to E is 1. Similarly, E to A is also 1, and node E to B is also 1. So B to E also is 1, and E to B also is 1. So in this way we can store the adjacency the information about edge in the adjacency matrix, and we will be using this in our coming lectures. So the fundamental way of the basic way of representing the graph is adjacency matrix, and nodes can further have properties which is known as the node features. We can see here, like this is the graph of social network, and suppose we have here, and this network consists of adjacency matrix which stores the edge information, and additionally the node come with its feature which we call the feature matrix. So each node will have its feature vector. We can see here that the adjacency matrix basically represents the structure, or it shows the structure of the graph, and the signal of graph is carried by, or it is represented by the feature matrix. So A represents the adjacency matrix and X represents the feature matrix. We can see the size of A is n by n, which means here n is the number of nodes or number of vertices, and here n also for feature matrix the size is n by f. Here n is the number of nodes and f represents the feature vector size, or the number of features each node consists of. So we can see, like here we have got a graph or the network of person. We can say it as a social network, and the feature the connectivity or the edges are represented by here by the adjacency matrix or the connectivity, and the feature vector or the graph signal or feature matrix or feature node features can be name, the age, gender can be its gender and its locality, and so on. So in this way we can represent the graph in terms of adjacency matrix and the graph signal. Let's see some more example of the graph. A simple example of the graph is a social network, or the graph available around us is the social network. Here we model this network as a graph by taking graph vertices or node as a person and edges as the relationship or connections between these nodes, or the persons, connection between two persons. Or here the edge feature is the connection between two persons, or for example in Facebook, if in this example, if Sam and Williams or Sam and Harry are friends, then they are connected, and they are connected, and the node feature consists of name, age, gender, and locality, and so on. So we can model this social network as a graph in terms of their connectivity, or the connectivity, and here edge features will be the connections and node features will be the name, age, gender, and address. And these informations or these data we can represent in terms of adjacency matrix and its feature matrix, or the node feature matrix. And another example of the graph data that's widely used is the brain connectomes. Here we represent, or we model the network, or we model the graph by using node as a region of interest, or the collection of tissues of the brain, and age represents the connectivity between those tissues or those region of interest. As earlier, the age features, here what we do is we use the structural or functional connectivity between those region of interest or those tissues, and node features can be taken as the volume of region of interest or volume of those region or tissues. And another example which is widely used, or as discussed earlier, is in the field of medicine or pharmacy. Here the molecule, we model the molecule as a graph, and here the node is atom, and H represents the bond between those atoms, and edge features is the bond between atoms, and node features will be the number of valence electrons, atomic number, and the metallic property, and so on. So in this way there are lots of other examples, and one simple example is even we can take image as a graph, but in image, like the nodes are represented by the pixels. We take pixels as a node and the neighboring pixels as the adjacency matrix, or the connectivity, or the here the one very special feature of image is that it's well structured, and the edges and edges are same for all nodes or